Hello and welcome to another wonderful magical Blender and Numpy tutorial. This tutorial we're going to be talking about slicing, fancy indexing, logical indexing, and if we have time, dot products, and we'll build a function closest point on edge. I don't know if we'll have time, but we'll see. So to talk about slicing, first thing we want to do is import Numpy as np. How do you spell import? There it is. And we want to build an array that we can play with. So we're going to say x equals np dot. We're going to just arrange some numbers here. And we want to do something that's divisible by 3 because we're going to be working with geometry later. And geometry is laid out in n by 3 arrays because each vertex has 3 values for its x, y, and z. So something divisible by 3. And I'm going to do 12. And the reason I did 12 instead of 9, when you do, like, let's say x equals np.arrange 9, and now you have these 9 values, and you want to look at it as an n by 3 array, so you do x.shape is 3 by 3, and then you look at x. Well, when you're doing specific operations, like say you're doing like a sum, and you want to sum the values on this axis or something like that, well, if your array is the same dimensions on both axes like this, you've got 3 by 3, you can easily get fooled and think that you're doing the sum on this axis when you're really doing the sum on this axis, and your math will be all screwy and it won't work. So whenever I'm doing experiments or testing, I always make an array that does not have the same number of dimensions in both directions, which is why I'm going to say x equals np.arrange 4 by 3 instead of 3 by 3. Or we could even do 5 by 3, so we'll do 15. So we want to do x.shape equals, what am I doing? 5 by 3. There. Now we have 5 sets of 3D vectors. We'll pretend like these are vertex locations for an object, like a plane with 5 vertices. There's a plane with 5 vertices. Pretend like this is the locations of each of these. It's not actually, but you know, we'll pretend. All right, so slicing. Let's say we wanted to figure out like what's the z-axis value, and we want to ignore all these other values. Well, we can easily get like every row, everything in the whole array by doing a colon. It just gives us everything. We've indexed everything. If we wanted to get like just the third row, we can do x2, and it gives us the third row, 6, 7, 8. Well, what if we wanted to get like a specific value? How do we get at these? I mean, you could do x like 0, which is the first row, and value 2, which is going to be a 2, and you get 2. You know, you could do the third row, 0, 1, 2, 3, and you do the second value, or index 2, and you get 11. So that's 11. And you can index it that way, but what if you wanted to get everything in the third, like, you wanted to get the third column. So for every row you want to get the third value. Well, you do the multidimensional slicing that Numpy allows you to do with Numpy array objects, which is really cool. So we want to do every row, and we want to get the third value at index 2. And that's going to give us 2, 5, 8, 11, 14. Ta-da! 2, 5, 8, 11, 14. And you can do x every value, you know, the first column, and you get this, you know, 0, 3, 6, 9, 12, which is here, 0, 3, 6, 9, 12. You can also do other kinds of slicing operations that are typical to Python, and you can do them in a multi-dimensional way. So, like, you know, a typical array, y equals np.arrange. Let's pretend like this is a list, and you just want to index like the values from 2 through to the end. So you do y, and you do 2 through all, and you get 2, 3, 4, 5, 6. Or let's say you wanted to index everything up to 4. So you do y and you do all through 4, and you get these 4 values, the first 4 values in the array. Now let's say you wanted to do that with a multi-dimensional NumPy array like this X array, and let's say you wanted just the Y and Z values. Well, you do X, so first thing you do is you say I want every row, and then you hit a comma, and I want just the Y and Z. So we're going to start at index 1 and we're going to go to the end. And that will give you 1, 2, 4, 5, 7, 8, 10, 11, 13, 14. 1, 2, 7, 8, and so on and so forth. And I've actually used this a lot in practical applications when I was doing like, in fact, yesterday I used it to create a UV projection for an application where I was pulling the 3D coordinates out and applying them to a UV map. So I just took the 3D vectors, I pulled the Y and Z values out, and then I mapped them to individual polygons. You have to do a little more futzing around when you're going from 3D vector arrays to UV coordinates, because they're for each face you have a set, and so things get duplicated. But basically, I just did this slicing operation, pulled the 3D coordinates out that I wanted, and applied them to the 2D coordinates. So, one other thing you can do with multi-dimensional arrays for indexing is to combine fancy indexing with slicing. So let's say I have an array of like 40 vectors, like from a Bezier curve. So we're going to do x equals numpy.arrange and some n by 4 thing. So we're going to do 5 times 4. Is that? No, that's not a 5. Sorry, 5 times 4. And we're going to say x.shape is also 5, 4 with an equal sign. And now x is going to be this 5 by 4 array. Pretend like it's a vector array for a Brazilian curve. Because for some reason Bezier curves have 4 values. It has to do with handles, and probably somebody else could explain it better than I could, and I'm not doing a tutorial about that right now. But anyway, it has 4 vectors. So let's say we wanted to get the Y and Z values of the vertices in this Bezier curve. Well, you can't just do like if you did X all through, and then you did like 1 through, and you're trying to get just the Y and Z value, you end up with the Y, Z, and W values. You get 1, 2, 3. What if I wanted to stop before I got there? I think I could do like, does this work? Yeah, you can do that. 1 through 3. So you could just get these values here by just saying, so I want to start at 1 and I want to end at 0, 1 at the third index. So you do 1 through 3 and it gives you, so remember x is this, and x, every row starting at value 1, stopping at value 3, gives you 1, 2, etc. So, and that's a really fast operation. Slicing is super high performance. It's like the fastest thing you can do with NumPy, so whenever you can slice to get at values, you should totally do it. But what if you wanted to get like 0 and 3 for every row? So the first element and the last element of every row. There may be a way to do this with slicing, but I can't think of it right now, so I'm going to show you the way that I normally do it, because I'm probably not smart enough to do it with slicing. The way that I normally do it is just with a combination of fancy indexing and slicing. So, quick review on fancy indexing. You use an array to index a subset of values. So like my Y array has these values, and this doesn't make any sense. So I'm going to say Y plus equals 7. Pretend it's a 7. And now Y is 6, 7, 8, 9, 10, 11, 12. So I want to get the second value, the third, and the fourth value of Y. I can do a list or a NumPy array or some other object with multiple elements inside of here to index those values. I want the 6, which is at 0, I want the 8, which is at 2, and I want the 12, which is at the very end. So I've got this fancy indexing array, and it's going to give me, theoretically, the 6, the 8, and the 12. 6, 8, 12. Yay, I looked at it right. Well, what if I wanted to do that on X? I have rows and columns and all these values. Well, I can do X, and I can do every row, and I'm going to get the first value at 0 and the last value at -1, because I'm too lazy to figure out that that should be a 3. So now I'm going to get 0, 3, 4, 7, 8, 11, and so on. Ta-da! I've indexed the element for each row at index 0 and at index -1. And you can do that any way you like. You could do, you know, -1, and let's also do 0 again, just for fun. And you can rebuild your arrays however you like by doing that. Keep in mind, when you do fancy indexing, you actually allocate new memory for the array. It doesn't just give you a view. Slicing gives you a view. It doesn't allocate any new memory. Fancy indexing is not nearly as high performance. It's still really fast because it's Numpy. It's going to be, you know, it's just light speed ahead of regular Python, but it's not as fast as typical slicing. So wherever you can slice, you should do that. When you have to use fancy indexing, you're still doing really good if you're using Numpy. All right. For the sake of understanding and clarifying, I'm going to show you something that's going to seem complicated at first, but will hopefully make sense in a minute. So we're going to do a new array. We're going to do a 3-dimensional array. So we're accustomed to our 2-dimensional array of vectors, which is, you know, n by 3. We're going to do like n by 3. So let's pretend like you had a whole bunch of triangles and you want to put them in groups. So we're going to do, let's say we have 5 triangles. So x equals, we're going to arrange here, np.arrange, and we have 5 triangles, and a triangle has 3 sets of 3 vectors. So 5 times 3 times 3. And then we're going to do, you know, obviously this is just a big bunch of numbers, but let's turn it into a group of triangles with 3D vectors in each one. So x.shape equals 5 sets of 3 by 3. And now you've got an array full of triangles, which whenever you're doing calculations on a big mesh, like collisions or things like that, the math is usually more efficient, or is often more efficient if you set things up in triangles, so it makes sense to look at sets of triangles. Well, what if you wanted to access like the z value in the 3rd vertex in the first triangle? Well, that would be, here's the first triangle, it's this set here, and it's the 3rd vertex, so it's this row here, and it's the z value, which is this 8. Well, you could just do, you know, x, 0, and 2, and 2 again, and that would give you 8, because you've just accessed the first triangle, the 3rd row, the 3rd value. And you can do that, and you can even overwrite it that way if you want to. You can do this value now equals 1,000. And now x, this 8 has become 1,000. And you're just overwriting one element in the array. When you do that, you're not reallocating memory, you're just overwriting it. So it's really fast to overwrite by indexing this way. You can also do slicing, where you could do like x, every value in x, I want to take the 2nd row, and I want to make, so you know, here's the first row, here's index 0, index 1, index 2. So I'm going to index this row for every group, and I'm going to make them all into 9s. X all, sorry, that's not what I meant to do. X all to equals 9. And now I should get, if I'm thinking about this correctly, these are all 9s, these are all 9s, these are all 9s, etc. So yeah, we've overwritten that set with 9s. Well, what if we wanted to do something even more complicated, like access every z value for every triangle? Well, we've got 3 dimensions here, and so you'll remember that this is everything. This is everything in the next row, and this is everything in the last, well, everything in the first dimension, everything in the second dimension, everything in the third dimension. So if I keep going, I mean, I can have as many dimensions as I want, and I can keep doing these sub-indexes into them, depending on how many dimensions the array is. So I've got x, all, and I want to do all again. So that should be a comma. So every triangle, I want every row, and then I want the z-axis out of each row. So I want to come up with an array that is 2, 5, 9, 11, 14, 9, 20, 23, 9, etc. Well, I do every group on the first dimension, every row on the second dimension, and then I want the z value, so that I will get 2, 5, 9, 11, 14, 9, etc. And I get, here's all the z values for each triangle. And it can get confusing working with stuff in this many dimensions, but I find it simplest to think about this is the first dimension, this is the second dimension, and this is the third dimension, and so on and so forth. So that's how you would index it, and that's how you would override it. Okay, the next thing I want to talk about, now that I've gone over that big complicated mess, is Boolean arrays, because logical indexing starts with Boolean arrays, which a Boolean array is just an array full of true-false values. And Boolean arrays are very fast for various things. They take very little memory. They're used for all kinds of stuff because they're cool, they're high performance, and they're just great for a lot of things. So first thing I'm going to do is create a Numpy Boolean array. So we're going to say boo equals, and we're going to make it the same shape. Well, we'll have the same number of elements that our x array has, which, what does x have right now? X has, well, let's rewrite x first to make this simpler. X equals np dot arrange 12, and x dot shape again equals 4, 3. Now x looks like an array of 3D vectors again, instead of an array of triangles. Alright, so let's make a Boolean array. So there's my Boolean array that I started. So what I'm doing there is just hitting up and down on the keyboard. The up and down arrow scrolls through all the stuff that you've already written, and you know, hopefully I haven't written anything in there that's like offensive or weird, and I don't think I did. Alright, so my Boolean array is going to have the same number of elements as x. I could actually do it boo equals np dot arrange, and we're going to do x dot size. Now if I did x dot shape, you get a tuple that has, 4 by 3. If I do, like, let's say I did, I'm getting sidetracked again. Let's say I did length, the Python's typical length function, x. Well, I get 4 rows because it gives me the length of just the first dimension. And that's not exactly what I want. It could be useful, but it's not what I want right now. Well, I'm getting sidetracked again. Let's say that I actually wanted that. Well, I could just do x.shape 0. And that's probably the fastest way to get how many rows you have in x, or what the size of the first dimension is, because it's just an attribute of x, and it's basically like a hash table to look that up. So it's a super fast way to get it. It's faster than if you did length x. I don't know if it's by much, but just for the sake of common practice, I prefer to use x.shape rather than len x, because I know it's a tiny bit faster. But back to what I was trying to talk about, if I can remember what the heck I was talking about, which was I want to get a bool array that has the same number of elements as x. Well, Numpy offers a really cool feature that doesn't care about how many dimensions an array is. It will give you the number of total elements that are in there, and that's just, you do x, any np array dot size. And in this case it would give you 12 because you have 4 sets of 3, and 4 by 3 is 12. So if I do np.arrange x.size, it would do 0 through 11, giving me 12 elements. I'm going to set the data type though so that it doesn't do that. I'm going to say dtype equals np dot bool. np dot arrange. Oh yeah, I can't do that. Wait, can I? No, I can't, because arrange gives me numbers in contiguous order, and I don't want that. I want to do np dot zeros. There we go. Now I have an array full of true-false values. And to look at them, I'm going to do boo.shape, make it easier to see, equals 4, 3. Alright, so here, and I printed x instead of boo. There's my array of values. And I can index this the same way I do anything. So I want to set all the z values to true. I would do every row, value 2, and I would say equals true now. And now the z values are all true. I think I can do like every value, the z, which is at 2, equals 0, and now when I look at it, it equals false. So you can put 0 in there. You could also put, like, I think you can put 5 in there, or whatever, some number other than 0, and it will evaluate to true. At least with Numpy, numbers higher than 0 evaluate to true. I think, like, let's see, numbers, like negative numbers, -1, also evaluates to true. So keep that in mind. 0 is false. I think pretty much everything else is true. Alright, now, what was the point, you may ask? Well, what if I wanted to use this logical index to access values in my x array of vectors? Well, it's really easy. You just do x and you do boo. And now I get, because it's true, 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 and it's just getting the z values, it pulls the z values out of the array, and it gives them to me. 2, 5, 8, 11. 2, 5, 8, 11. So this array here is taking all these trues and it's pulling all of these values because these trues correspond to these values. That's cool and all, but you may wonder, well, what's the point? Well, what if you wanted to access all the values that met a certain condition? Or like, let's say you wanted to access all the rows that met a certain condition. So, well, it's easy. You write a logical expression. So let's say that I had a cube. Let's pretend like I just added a cube to the scene, which I did. And let's pretend like I wanted every value that was less than 0 on the z-axis. So like, you know, maybe you're making a video game and you have a pool of water and you want to know what parts of the mesh are underwater and what parts of the mesh are above the water. Well, the water is perpendicular to the z-axis, so all you have to do is take the z values and figure out which ones are below your plane. Now my plane is currently at 0, 0, 0, 0, so all I need to do is find out which values in this cube are less than 0 on the z-axis. Well, with Numpy, it's really, really easy to do that kind of stuff. So here's my x array. I want to find out which values on the z-axis are less than 0. So first thing I'm going to do is find the values on the z-axis with slicing, which are these values, the 2, 5, 8, 11. And then I'm going to say which ones of these values are less than 0. And I will get a Boolean array. X all for 2 is less than 0. In this case, is 2 less than 0? No. 5, 8, 11, no, none of them are less than 0. So obviously they're all false. But if I did less than 8, then I would get the ones that are less than 8, which in this case are 2 and 5. So true, true. Now let's say that I wanted to access every row that has its z value at less than 8. Well, it's really simple. I do x all for 2 is less than 8, and I want to use this to index x itself. So I'm going to say, give me the rows that have a z value that is less than 8. And what it does is it gives me the first row and the second row because it's taken the 2 here and said the 2 is less than 8, and the 5 here and said the 5 is less than 8. So it'll give me the whole row for those. It's the same thing as if I did, like, let's make this a Boolean array first, so this is a little easier to see. We're going to say boo equals this. Now, boo equals x less than 8. Yeah, I forgot that thing. So boo is now this array with true, true, false, false. And I accidentally put it in parentheses because I got my syntax wrong. Or sorry, in square brackets. So we're just going to try that again. And we're going to say boo equals this. Alright. There we go. Now here's our array that's not wrapped inside of a list. So true, true, false, false. And now if we index x with boo, we get our first 2 values. Now let's use it in practical geometry. Alright. In our second, I believe it was, tutorial, we talked about accessing and manipulating geometry. So we have this cool thing that lets us take whatever our active object is. So this gets coordinates and converts them into an n×3 array of vectors as a Numpy array, and then I was using it on cool stuff down here. So here is my coordinate set. So we're going to go ahead and right here I have print CO, and then I don't know what all this stuff is, but I'm going to get rid of it for now. And then, so all we're doing is we're going to print the coordinates, and then this is actually writing it back so that we could do some kind of an operation on it. So over here is where my output is. And if I print the coordinates of what is the active object in the scene, then I get these cool sets of -1s and 1s and everything. And, you know, if you move this, you get an array full of scary numbers that I like better for some reason. I don't know why. And if I wanted to transform them, I could do, so I'm getting the coordinates with this function here, and I'm calling this function right here, getCO. Right here I'm printing it, which gives me this, which is the location of every vertex in this cube object. And now I'm going to like add something to it. So I'm going to say CO plus equals 2. And what that's going to do is it's going to add 2 to the x, y, and z location of every vertex. And so it's going to move diagonally when I do that. So it moved, and it's just going to keep doing that for as long as I keep pressing that. It's moving diagonally. It's printing out the locations and new locations every time I do it, and so on and so forth. Alright, so now I want to figure out what parts of my cube are underwater. And there we go. So we know that part of the cube is underwater when we look at it. Now we want to do that with the logic. So we're going to go, first we need to grab the z values of my coordinates. So we're going to use slicing to do that. So we're going to say CO, and we're going to do every row and the z value of every row. And just for fun, we're going to print that. So you can see here's the z values in a flattened array. And now we want to do, we're going to say z equals this, because this is my z value. Alright, there's my z values. Now I want to get a Boolean array, so I'm going to say boo equals z, which is less than 0. Now if we print boo, we'll get an array that has, you can see that 4 of the vertices in this cube are below 0 and 4 of them are above 0. So we should get an array with 8 true-false values, and 4 of them will be true, 4 of them will be false when we print boo. And you get true, false, true, false, true, false, true, false. Exactly like I thought. Something else that's really helpful, there's an add-on called Measure It, and I think it's actually packaged with Blender. You can just go to add-ons and search for it and enable it, and it will bring up this really cool set of tools. It has these things for debugging geometry inside of Mesh Debug in the Measure It tool set, and you can turn on like edges or faces. You can set it to be selected or whatever, and then when you click on Show, it will take whatever's selected Actually, do I have select set? I don't know. Anyway, it lets you see the indices of each vertex. So remember, 0 is below 0, 1 is not below 0, 2 is below 0, 3 is not below 0, and so on. So this is another way of helping you visualize what the heck is going on here to enable the mesh debug in this measure it tool. I use it all the time. It's a really cool thing. Alright, so now let's do something with this. Let's say that our cube is scared of water. So every part of the cube that is underwater, it wants to get out of that water. So we're going to say, first of all, we need to find everything that's underwater, which we've done here by saying, here's all my z values, here's an array that tells me which z values are underwater, and now we're going to access every one of those vertices that's underwater, and we're going to tell it to get out of that water. So first of all, we need to say, well, which direction do you want to go to get out of the water? We're going to make a Numpy array. So escape z, because it's, well, let's say don't drown, or no drown. U-N-D, is that how you spell it? I don't know. I always Google the spellings of stuff. No drown equals np.array, and it's going to be, we don't need to move on the x-axis, we don't need to move on the y-axis, we need to move on the z-axis. So it's going to be 0.2. Just because I just want it to move a little bit, it's going to have to work at it. You know what, let's make it even smaller. 0.1. It's going to really have to work to get out of that water. No drown! Alright, now we want to say my z values for CO that are below water, which we've already created this Boolean array to tell us which vertices are below water. So now we're going to access every vertex with that Boolean array. And we're going to say CO, this set, plus equals, no, not plus plus. What is this, C++? No, this is Python. Plus equals no drown. Yeah, there we go. Alrighty. And now, when we click on, when we run this, the values that are below water are going to start trying to get away. They're like, help, get me out of this water. And they're like, oh, we made it. So now they're out of the water. They can stop panicking. But what do you say? Wait a minute. Something's happening. We're going back underwater again. Oh no! What the? Ah! Wait, is that working? Is it going down? Why isn't it going down? Oh, I know why. Because they're still below z. So it's like, see, we're not underwater. We don't have to move. But you are underwater again. So now we're going to go back down. Everything that's below z is going to be going, oh no, we're sinking deeper and deeper. Now, obviously, oh, like I forgot to move those guys, or this guy thinks he can escape. Ha, now you're drowning too. Alright, now this is useful obviously for a lot of stuff, but what happens if the world is tilted? And we want to know, like, stuff that's below z now on this, and this plane represents our water. Well, it's not aligned to the z-axis, it's aligned to some weird axis. Well, what the heck do we do there? What if we wanted to figure out what's on the other side of this plane, but this plane's not pointing on the z-axis? Well, we can't pull the x or the y or the z. That's where closest point on edge comes into play, because you can use the closest point on edge function to figure out where something is at in relation to the normal of a plane. You can use it for all kinds of other cool stuff too. But this tutorial is pretty long already, so in my next tutorial we'll get into closest point on edge, which means we will also talk about dot products and possibly even Einstein summations. I know it sounds like a big word, but Einstein summations is just a fancy way of multiplying and adding arrays of vectors together with matrix operations, which I guess that sounded pretty complicated too. Basically, I use Einstein summations for dot products. And I will hopefully cover that in the next tutorial. Thanks everyone for watching, and we'll see you with Einstein summations.